Okay, hello, welcome to mygeekyhobby.com. Again, today we are going to be looking at some work in KiCad. I'm pretty sure that a lot of you who are tuning into my channel have probably experimented with KiCad before. For those who are pretty new to KiCad, there's plenty of videos on YouTube that cover KiCad very nicely. KiCad is a package for designing PCBs, and that's what we're going to be using today. But today we're going to be taking a slightly different approach to KiCad. And what I mean by that is today we're going to be trying to adjust a design that was originally intended to be manufactured professionally by one of the PCB manufacturing companies. I often use PCBWay, but what we're going to be trying to do today is adjusting a design so that we can manufacture it at home. Now, manufacturing at home, you would be probably asking yourself, Chris, why on earth would you try to manufacture something at home if getting a PCB made today somewhere in China is very cheap, and it doesn't even take much time to get it made. Yeah. So probably it's not really such a great idea to do the manufacturing at home, and I normally don't do it. I send all of my designs to be manufactured. But occasionally you might have a situation where you actually do want to have, or you do want to make a PCB at home. Two examples come to my mind. Why would I want to have a PCB manufactured at home? One of the reasons is maybe urgency. Maybe you're working on some design and you really want to very quickly get a PCB. I know that with express shipping, you can have probably a PCB made and shipped to you within a week. But what if you want to have it today or within a couple of hours? What I have here on my desk is a small RAM tester. It's an open source design. I'll share the website soon where I got it from. But see, this is something that I very quickly put together to test some RAM chips. I want to turn this into a PCB. Of course, I could send it to be manufactured. Imagine you sending something to China the week of Chinese New Year. You're going to be delayed. It's going to take 3 weeks before you have the PCB. But I want it today. I want the PCB now. So how can I have it manufactured at home? So that's what I'm going to be talking about today. I've been manufacturing PCBs at home since I was a young kid. In fact, this is probably one of my very early homemade PCB designs that I've made. I do have a timestamp here. It's 1999, so this is when I built this specific PCB. So I do have quite a bit of experience of doing it at home. I haven't done a homemade PCB for probably 20 years. So it's going to be a sort of an exercise of trying to remember exactly the process. I do have actually additional motivation to do it at home. I'm recreating, or I'm trying to redo a design of an old computer, one of those 80s computers, and that computer was also sort of homemade. So I want to recreate that PCB at home, and I want to have the whole thing homemade. That PCB that I'm planning to do is pretty big. So I thought, let me try to do something small first, sort of get myself up to speed with the process once again. So that's what I'm going to be doing today. So the intention for today's session is to turn this open source design. There's actually a PCB with this that comes with this design that is already designed, but we're going to do some changes and we're going to adjust that PCB so that it can be manufactured at home. So let's head to the computer and I'll show you the project that we are going to be trying to adjust. So the project is published on BitWrangler's website. It looks like he's a fellow retro computer enthusiast. So he published this 2114 SRAM tester. Looks like he was trying to fix his ZX Spectrum, and he needed to test the 2114 memory chip. I do have a couple of computers that use this chip, and one of them also is a suspect. So I thought, why not design myself that, or build myself one of those testers. So as you can see, he published, he's got a nice PCB that comes with his project, and awesomely, he shared the design on GitHub. So all of the files, the Gerbers, the schematic is available on his website. So I'm just going to download this whole repository, and then we'll head to KiCad, and we'll open the project in KiCad. So this is his design. I opened it in KiCad 6. His design is in KiCad 5, but it doesn't matter. It's just going to be converted or upgraded to KiCad 6. So if we just very briefly take a look at the schematic of this project, it's super simple. It's pretty much an Arduino Nano, and all of the pins of Arduino Nano are routed to pins of the socket that the RAM chip is going to be inserted into. There are some status LEDs and a push button. Very simple. So from the schematic point of view, there's not much we need to do. What we probably want to do is take a look at the printed circuit board, which is here. So why do we even want to do anything with this printed circuit board? Why don't we just take whatever he's done and try to manufacture it? So of course, with the home manufacturing methods, there are some limitations that we have, and this design that he's got here is really aimed at a professional manufacturing shop. A couple of things that will be a problem for us is, for example, this design is dual layer. So you got a PCB tracks on the top layer and on the bottom layer. We could do 2 layers at home, but it's so much more complicated, and the design is simple, so we shouldn't, this doesn't have to be so complicated. We can definitely adjust and make it easier for us to actually manufacture. So with those limitations in mind, I'll try to do a couple of adjustments before we head to the actual, before we attempt to manufacture this design. So what else, what other things we probably want to adjust? For the home manufacturing, I don't like the fills. So all these areas here are fills. It means that all this stuff is going to be filled with copper. I'm gonna, as a first thing, I'm gonna pretty much delete all those fills. I don't need the fills. They are so much more difficult to manufacture if you have the fills in. What else? As you can see, the tracks are on both on top layer and bottom layer, which is going to be a problem for us. So in reality, I probably want to start fresh with all the tracks routing, because this is just going to be too difficult to deal with the way he's got the design. So what I can do in here is probably get rid of all of his tracks and then start routing my own tracks and making the adjustments based on what I feel is a better way of doing it. And again, this is purely because I'm going to be doing it at home. I'm going to be doing the home manufacturing approach. So what we'll do is we'll disable footprints on this view. We'll remove. Yeah, okay, we can do like this, and then I can simply select everything and remove, and this will get rid of all the tracks. Of course, all the components are still there, and as you can see, after doing this change, we see the rat's nest of all the connections that we need to route. We still have all the components on this PCB. So the next thing we need to do is start laying tracks. and trying to adjust the design. So what else can we do to make the track laying a little bit easier for ourselves is a couple of things. First of all, if you look at this rat's nest of connections, if you take this socket for the RAM and kind of move it around, you will see that pretty much all of those connections are crossing each other. Crossing connections, it means that it's going to be hard to lay the tracks without using jumper on another layer, or without going between. I mean, this is going to be very complicated. So just by simply rotating this socket, we can see there's so much less of the connections that cross each other, and that means it's going to be so much easier to ultimately lay the tracks. So that's the first thing I've done. I've swapped around the that socket. I'm gonna make a little bit more space for myself here with those LEDs. I don't like the fact that this resistor is sitting here and we've got another couple of resistors at the top there, so I'm just gonna sort of move this around, and I'll probably pull this switch a little bit higher up. So with those, one more thing that I'll do is probably move this to be in line. I'm aiming for as many of the rat's nest links to be sort of straight, so that we can easily route some of the connections. So that's the first design. So what you're trying to do is to sort of logically position the components the way that the actual tracks that you're going to lay later are going to be much easier to route. As you can see, I have quite a few of those straight links, so that they should be pretty easy to actually perform. So that's placement of the components, which is a very, very important aspect of this whole thing. The other aspect of the design is the actual pads that we have in this design. And what I mean here is, if I take you back for a moment into my desk, let me show you. This is this is just a PCB, professionally manufactured PCB. What you will notice is that a typical pad is plated, which means there's a metal in between the top and the bottom layer. That metal, when you start soldering, gets filled with solder, and that's actually what gives majority of the strength of the connections for a professionally manufactured PCB. But when it comes to those homemade designs, you don't get the through plating, which means that you really need to put as much area of the pad on your bottom layer as possible, just to give your components a space, or the solder and the component, they need enough space to actually work together. So they need to have enough space to give the connection strength. It's not just the strength, it's also the ability of the copper to stick to the substrate. If you make the pad tiny, it's gonna be hard to hold the actual copper track onto the PCB. If you overheat it, it will start coming off. So what we need to do is we need to adjust those components and give them a little bit bigger pads. Those pads here are way too small. There's a number of ways you can do it. What I will do is I'll double click on, for example, this Arduino module, and in here you have the ability to edit the actual model that you've got in the library, or you can edit this specific component that is on your PCB. So I'll just select Edit Footprint, and what this will do, it will open a component editor in KiCad. And it will allow me to adjust this one component in this design. Let me just bring the editor. It's still loading. Don't know why it's taking so long. Let me bring the editor to the other screen. So that's our component, and what we want to adjust is we want to adjust a little bit those pads. So let's click on one of the pads, and let's change the size here. I've got some of my nodes. I'll do 013, and the other one is fine. Okay. So what this does, it creates a little bit more area of copper, so that our soldering later is a little bit easier, and we give this pad more strength to hold to the substrate, and also for the solder to have a really good contact with the actual pin of the component. Of course, I don't want to adjust every single pin by hand. In KiCad, you can right click and you can select push pad properties to other pads, and we'll just let the KiCad adjust all of them. Of course, this one only adjusted parts of the same shape and size. We have one, typically pin 1 is different shape, so we're just going to adjust this one as well, and we'll do it by hand. Okay, so that's our Arduino module done. We adjusted the parts. Oh, sorry, I forgot one more thing. This hole that is in this design is too large. We don't need it to be that large because we're going to be drilling by hand anyway, but we want a pilot hole so that our drill can hold to something. So I typically do 0.02 like that, and again we're just going to push this change to all the other pads, and we're going to adjust this one to 0.02. Okay, so that's our Arduino module updated. It has smaller holes here for the drill, and it has larger holes so that our soldering is easier. So you can save and close this. And as you can see in our design, this has now been updated. Let's do the same thing with the other components. So same thing, edit footprint. This will open the footprint editor. Double click on the pad. We'll change this to 0.13 and the drill size to 0.02, just like that. Right click, push to other, and then the last one is this one. It needs to be adjusted by hand, and 0.02. Okay, save the component, close. Okay, so I'll skip the rest. I'm just going to quickly adjust the rest of the components. So same idea here. You know, you don't want those holes to be that large, and you want a little bit more of the area so that you can solder it easily. I'll be back after I quickly change the setting. Okay, so the design has been now adjusted from the parts perspective. So the only other thing that we need to do now is to route all the trucks. So let's give it a go. We're going to be routing majority of the trucks on the bottom layer. So that's what I'm going to do. So let's just pick a truck and try to route it and see how it goes. So we have a couple of obvious ones. So we can run a truck from here to here. Now, obviously this truck with the die that okay, so that's 1, 2, 3. So those are some of the obvious ones, some of the easy ones. Okay, so I'll very quickly route the rest of the PCB. You can watch, I'll speed up the whole process and we'll analyze at the very end. There is one or two spots where I just want to quickly show you a few tricks or a few things that you might want to do as part of the design. And then we'll kind of reveal the final product. Okay, so at this point I've got a couple of more tracks to lay, but I decided to stop here and give you a couple of more examples of what you can do to make the design or to make the the manufacturing a little bit easier. So I've got one more track that I need to run between here, this power feed, and probably somewhere. Where is my power? Okay, so if I highlight this track, I can see that ultimately I need to either somehow go all the way to here or somehow all the way to there. So let's do it with a jumper lead, or with a lead that will do on the other side of the PCB. So what I'll do now is I'll run a track, and what I need to do is I need to somehow get from here across this this track that is in my way, which means I'll place a via here. I'll go to the other side, and I know we're not manufacturing a double-sided PCB, but we can run a piece of wire, like a jumper wire between. So we're just gonna so to do that, we're gonna make sure that this track is actually just a straight track. We'll place a second via here, and we're gonna finalize our connection into here. It's a bit ugly, but let me just rearrange it. Okay, so what this means is that we're going to have just a single link of wire that we'll need to run on the other side of the PCB to run this link. Don't forget about adjusting the sizes, because that's, again, you want to be able to actually physically manufacture this PCB. So even those vias, they need to be large enough so that you can actually do it. So that's, oops. Let me see, can we copy it? No, let's just adjust the size, 0085 and 002. So that's one part of our design. We have another one here that is the same sort of problem. We'll run a via here and go to this layer, and we'll finish here with a via. Okay, so that's a single link of wire to create those connections, 0085 and 002 for here, and 0085 and 002. Okay, so most of our routing is done. It says we're missing a connection here to the ground. In this design, those grounds are already connected on the actual Arduino module. So the flexibility of KiCad is such that you can simply flip to the schematic diagram, and you can say, oh, I don't need whatever connection. This is pin 4. Let's just say pin 4 doesn't have to be connected to ground, because in fact it is connected to ground internally. So I'll just remove it here, and I'll place a no connect indicator here. Save it, and then we can update the design from the schematic, and as you can see, that that's not there anymore. This rat's nest link is not there anymore. because I was just quickly running those tracks so I can record the video for you. I'm not making it super beautiful. In a moment, I'll show you the final design that I have or that I came with. But I'll typically kind of rearrange those things to make the spaces, the spacing kind of equal, to make it a little bit easier to ultimately manufacture. You don't want those tracks to be so close to each other, so I would do a couple of more of those adjustments. Let me save this. Let me actually load up the final version that I came up with. 1 second. So here is the final design. You will notice the one thing that I've done is I also flipped the whole thing on my screen 180 degrees, so that I sort of like to have this focal point of this design, which is the socket for the actual RAM that we're testing. I want it to be facing up, so I don't want this to face down. I typically put all of my chips facing pin 1, facing up, wherever I can, obviously, in the design. But that's the final, that's the final design. We have the few links that will run with a piece of wire. We have the tracks finalized. So now it's the point where we need to try and do the actual manufacturing. There's many different methods that you can follow. I use the ink transfer method. They are pretty well documented on the internet, on YouTube. So I'll just very briefly show you my process. I'm not going to go into too much details, but ultimately that is the design I'm gonna use. So first thing we'll do is we'll print this design on a piece of paper. So first we'll print it just on a piece of paper. We don't need to print it mirrored because we're printing the bottom layer, so we can print it just the way it is right now. Few notes about the printer. I use just the ordinary black and white old HP printer. It kind of gives out quite a lot of toner. It's the printout is very intensive, so that's I found it to be a really good printer to do this toner transfer method. So we'll print a copy of our design on a piece of paper to start with. Okay, so now that we have the design printed, let's take a look. So the two reasons you do this printout. First of all, to kind of manually verify if everything looks good. And as you can see, I'm pretty happy. This design seems to be fine. There's nothing really standing out. All parts are large enough, tracks are wide enough, so that should be a good design. Of course, I said we're going to be doing a toner transfer method, so we need some paper or some way to transfer the toner onto the PCB. I'm using this special paper, this toner transfer paper. It's still available. I've seen it. I mean, I bought it obviously in US, but you can buy it in other places. I've seen people commenting that other paper is also usable. Just check other YouTube videos if you're really trying to do this. I found that this paper is really good to do it. It's pretty expensive, so I don't really normally want to print a small design like this on a large piece of that fancy paper. So what I do at this point, once I know that the design is, printed on a normal paper and it's fine, what I will do is I'll use a bit of that special transfer paper. I'll trim it to the size, like in this case, to the size of the PCB, and then I will secure it with a bit of sticky tape to the edge, just on the edge, and with that is enough for me to later feed this whole thing into the printer as a manual feed. This will allow me to, do this printout, just wasting a tiny little bit of this fancy paper, and it will be ready to go. So let me do that. Let me send this to the printer, and then we'll take a look how it looks like when it comes out of the printer. Okay, so this is the printout as it came out of the printer. So as you can see, I've only wasted that small piece of the fancy paper to do this design. So I can now sort of take it out of here, and this is ready to go. All I need to do now is to prepare the actual copper clad PCB. I'm going to use an iron, normal household iron, iron it on, and then use some water to remove the top paper and then etch it in just the ferric chloride, and it should be ready to go. Let me show you a little bit of that process very briefly. So for our PCB, I've got just a copper clad FR4 cut to size, dibber a little bit so it's not sharp, doesn't have sharp edges. Depending on where you get your FR4 from, sometimes it can be quite shiny and sort of hard to transfer the toner. So I often run a bit of sandpaper, fine sandpaper on it, just to kind of give it a little bit more, improve a little bit the ability of the toner to transfer from the paper onto the PCB. So there'll be some fine dust, copper dust on the PCB as well. You want to make sure you wipe it a little bit, and this brings the PCB sort of to the point where it's ready to do the transfer. Like I said, I use a normal domestic iron, clothes iron, to do this. The people that sell the paper, the company that sells the paper, they have the process pretty well documented. They recommend, they have a set of recommended tools to use. Like I said, I only do it very rarely, occasionally, so I have my favorite clothes iron, and I have the process roughly figured out, so it's repeatable for me. So this video is not really meant to give you very deep insights on how to do this toner transfer process. There are better videos and websites that describe all of this in detail, and I would recommend you follow that. What I'm showing you here is just a brief version of what I do, and this will show you the final results quite nicely. Okay, so we'll put our design on the PCB just like that. As you can see, I made my PCB a little bit bigger than I need to, but it's fine. Sometimes the transfer on the edges of the PCB can be a little bit tricky if you're using iron like I do. I put a piece of paper here to make the ironing a little bit easier, and I simply just iron it on. There's a bit of a process of figuring what is the best temperature, everyone's approach or everyone's iron and PCB thickness and paper, and there's many different factors that will have influence on your final result. So you may have to experiment the first couple of times, but for me, roughly that's what I do. I just use the iron and kind of run over this thing. I put a bit of pressure onto the paper. Ultimately, what we want to do is we want this toner to stick to the PCB. So the toner needs to get to the point where it is sort of melted, but not melted too much, because if we melt it too much, it will smudge, and it's not going to be a sharp impression. So it needs to be, all the parameters needs to be a little bit adjusted. So like I said, you may have to experiment if you're doing it for the first time. You might not get the best results the first time you do it, but once you kind of adjust your parameters, the method, the process is sort of repeatable and good. Obviously you're dealing with a hot iron. I've got a silicon mat on my desk, so that's that's fine for me, but be careful where you do it, how you do it. And this is all sort of experimental, so hopefully we'll get a result this time, a good result this time, but I'll let you discover it with me. Okay, this is still very hot, but the idea now is to soak this in a bit of water. And the paper is covered with some substance that will dilute in water, and the paper should release the ink, the toner, and we should be left with just the toner on the PCB. As it always happens, when you do it in front of a camera, it might not work the first time, so I'm just gonna hope for the best, but if needed, I'll just repeat the whole process so that we have a working PCB. Okay, as you can see, this has been somewhat successful, and what we're left with is a PCB, is this copper PCB with our toner transferred on top. Okay, so we're happy with this. Next step is going to be etching. Let me prepare everything for etching. So what we're going to be doing for etching, we're going to be using a bit of this ferric chloride. I got it from MG Chemicals. Of course, we're dealing with chemicals here, and this thing will stain everything. And obviously it's not good for your skin, so make sure you've got protection. And I'm just gonna dunk this PCB into the ferric chloride. And I mean, there's different methods of doing it, and everyone has got their own ways of doing it, but I'm just gently stirring it until I see it's done. So bear with me, I'll speed up this video and show you the last moments when we are almost done. Okay, so our PCB is almost cooked, almost ready. On my desk under the camera, I'm not able to heat up or warm up this solution. Normally it's a little bit faster if you are able to keep it warm. I typically have it in another dish that is getting warmed up, so that we can keep the whole solution a bit warmer. That means that it's etching much faster, but it's kind of ready at this point. As you can see, all the copper that used to be there is now etched away. So I'll take it now to rinse, and I'll bring it back in front of the camera. Okay, so after rinsing it in water, I also used a 600 grit sandpaper to remove the toner. You will notice that the tracks are not perfectly smooth. I see a little bit of pitting. What probably happened is maybe I didn't press the iron hard enough, and the toner didn't fully transfer in some spots, but it's still usable. I still believe it's gonna be usable. So typically what I will do next is, the moment you finish sanding this PCB, it starts oxidizing. So I will normally put a little bit of flux paste onto the copper tracks. First of all, to stop them from oxidizing. And second, we will use a little bit of solder, and we'll just simply tin with solder. We'll tin this PCB so that all the tracks are tinned with solder. Let's I'll just use a soldering iron and do the tinning this way. And with enough, if you put enough flux, the whole process is very quick. And I just simply run it this way. I have a soldering iron with a pretty wide tip. This will keep the tracks nice and shiny, and it will stop the copper from oxidizing. And later, when we start soldering, it will actually help us with the soldering process. Alright, that's done. We can use a bit of isopropyl alcohol, wipe the flux away, and this part of the process is done. Of course, we also need to drill all the holes. I don't have any fancy drill. I just bought this cheap drill on Amazon. I'll show you, but I wouldn't recommend because it is actually a pile of garbage. It's kind of wobbly, so it doesn't really do a good job. put this PCB on something that I don't drill into my desk. So literally now it's just a case of drilling the holes. And I can do it by hand, you know, I have some dexterity, so I don't need any other stand or anything like this. I just do it by hand. As you can see, all the holes are coming through nicely. So I would do, you know, for the sake of finishing this video on time, you know, I'm not going to show you the whole process, but ultimately I would drill all the holes, and with the magic of movie making, that's the final result. The same method I used to do the tracks at the bottom, I used the same toner transfer to do the lettering at the front. Just to make it a bit easier to recognize what's what, you know, you got the LEDs, the button and stuff like that. Yeah. So, you know, ultimately after soldering, we only needed to do one link or two links here for those two connections. And, you know, that's the ultimate final result. So as you can see, you know, it's usable project, took maybe 2 hours all in all to complete it end to end. But we can have it, you know, have it here and now, as opposed to waiting 2 weeks for the PCBs to be delivered. And like I said, the other motivation I had is I will be building this homemade computer, and I want it to be homemade. I don't want to manufacture the PCBs for that computer, so I use this as an exercise to get myself kind of ready for the big project. So just for comparison, side by side, 1999, 2023, very similar results. So that's my method of adjusting KiCad KiCad designs for manufacturing at home. Thanks for watching. If you enjoyed the video, obviously give it a thumbs up, and subscribe if you don't mind. That will help me build my channel and grow my channel. I'll see you on the next one. Thank you.